Also, trainees.
Yeah, I am. What's your name? Where are you from?
One more guy is in control.
Yeah, I saw him when I was upstairs. Oh, this doesn't.
We all set, sir. We all set.
The site change it doesn't work?
Yes, just yes. All set.
Yeah. Okay. So I'll start whenever. Okay. Sure. Unfortunately, you have to wait till then your photograph comes through. Yes. You what you're doing. Good. No, but you still have 1.5 assignments to finish, not just. Yeah. I'm set. Google copyright violation. Some student or some visitor got it on some Google image when I typed in ICTS. I kept this reason. I think in Kharagpur I put this in just to advertise it, and then I decided to keep it. Yeah, sure.
All right, everyone, welcome back to the last part of today's program. We are very pleased to have Professor Samriddhi Shankar Rai from ICTS, and he is going to talk about bacterial or active turbulence.
Thank you. Let me begin by thanking Tapomoy, Sumantra, and Christina for the invitation. Actually, when Sumantra asked me a few days ago to give a talk in this meeting, I was quite hesitant. And the reason for that is I work on turbulence, on what are sort of high Reynolds number inertial turbulence. My knowledge of active systems won't last the full hour, so I won't go till the bitter end, but I'll sort of finish hopefully well before that. But recently in our group, we've been looking at a very small sort of, corner of this wide class of problems at the interface of physics and biology. And let me try and sort of tell you a little bit about what we've been doing. So, so that's sort of the apology or the disclaimer that although I'll be talking about low Reynolds number active suspensions, the approach is one that's really coming from the gaze of someone who does high Reynolds number turbulence. So, there will be a bit of complex environment for sure because it's turbulent, and we'll see how much of real active matter still persists. So, as all of you know, over the last 10 days, this is just for the sake of completeness, for someone like me, active matter is ubiquitous. And more importantly, for me, active matter is all matter that moves. So they're sort of out of equilibrium, and they're composed of agents which consume energy and they move. And it sort of spans across several length scales. So those of you who will be here next week, you'll, some of the sort of names or ideas that I'm going to talk about, you will hear much more of that from the experts next week. So in this talk, and this is, sounds a bit presumptuous, but that's all that I've worked on in active systems. So in this talk, I will essentially focus on dense bacterial suspensions. So these could be suspensions of either B. subtilis bacterium or E. coli bacterium, and you'll see why I'm sort of flagging both. What you will also notice clearly is that very soon much of the essence of the bacteria will get washed away from what I'm going to discuss and talk about. So these bacterial suspensions, and this goes back to this very nice paper 10 odd years ago by Wensling, Julia Yeoman, and others, where they looked at this sort of dense suspension, and this was Bacillus subtilis suspension. The details are all here. The essential point is that these are swimming. So this dense suspension is a two-dimensional fluid, if you like, where the fluid is that of these individual bacteria with these properties. But these are flows which are at very low Reynolds number, far away from my comfort zone. But what they did notice, and this is sort of obvious to people, if there's anyone in the audience who has ever looked at real turbulent flows in 2 dimensions, what they noticed was that these tend to form patterns which are very similar to what you would get, for example, in a 2-dimensional turbulence system. So this could be a soap film which is agitated so that it's turbulent. So this is at Reynolds number close to 0. This is at Reynolds numbers which are very high. So this sort of analogy between these two figures, if you like, sort of gave rise to this whole field of, to the best of my knowledge, this whole field of active turbulence, which essentially concerns with the dynamics of low Reynolds number active suspensions and the fact that they sort of reminds one of vortical chaotic high Reynolds number turbulent flows. And so this is really the starting point for us. And there are a couple of very nice review articles from where we learned some of the tricks of the trade. So how does one begin to even sort of conceptually model such a suspension? Sigda sort of talked about it at length from various aspects this morning, so I'll just take it up from where she left, essentially. So the simplest way to model such a suspension would be, for example, to use these what are known as agent-based models. So you essentially take a bunch of particles. These particles may perhaps move with a constant speed. You specify its direction. You add a little bit of noise. And essentially, when you put all these factors in, the sort of Wicksec-like examples that Signa was talking about, you end up getting beautiful sort of flocking behavior in these systems. And so sort of this work, of course, goes back to this sort of fundamental paper some 25, nearly 30 years ago by Vic and others, who sort of showed that there is a novel type of phase transitions in these systems, and essentially just simple agent-based models give rise to an emergent collective dynamics, which is quite interesting. So more recently, I'm not going to talk much about this, but more recently, using similar microscopic approaches, so complex environment, we have been sort of looking at the motion of swimmers in essentially a high Reynolds number turbulent flow to actually understand if turbulence can, in some way offset the degree of flocking, because we all know that turbulence leads to enhanced mixing. So are there ways in which the right size, the right shape of sort of micro model, micro swimmer actually matters for one to sort of see these nice flocking behavior. One can also extend this. We've been sort of looking at these filaments, which are essentially simple sort of bead spring model, if you like, or some sophistication of that, but not much really, which also, so the background here, if you wish, is high Reynolds number water. So let's say this is, in a pond, in a marine environment, which is really turbulent, where either these sort of chaps are swimming or flying, or these sort of filamentary objects are moving. So the microscopic approach, of course, several people, and some of them, will be giving lectures next week, also incorporates more realistic models of these sort of active matter, where you sort of think about self-propelled rods. You actually incorporate more of the physics, more of the biology, more of realism in trying to model these systems, but building up from a microscopic picture. And so you can sort of think about polar particles, apolar particles, self-propelled rods, all of these, and they sort of tend to give you several different kinds of ordering of these particles. So that's not what we are going to talk about in this today for the next 40 odd minutes. What we are going to do is basically look at this. So this is a sort of movie from experiments that we are currently doing on E. coli suspensions, where this is a bunch of bacteria which are swimming, again, very low Reynolds number. But when you actually look at this movie, you realize that probably it's possible to have a more fluid-like description. So you can sort of come up with hydrodynamic descriptions. You coarse-grain this field. You forget the individual bacterium, the rods or the sort of apolar-looking sort of needles and stuff. But you probably might want to write down a continuum description of this, and that's what this talk will be about. 2D. 2D, yeah. So 2 plus half a body width of the bacteria, right? All right. So, all right. So essentially, what this sort of suggests visually is that these dense suspensions can lend themselves to a continuum description, and once you have a continuum description, essentially you're writing down a coarse-grained velocity field. So you have a velocity field u as a function of x comma t. And the next stage, of course, is to write down the differential equation, which will govern the evolution of this velocity field. So what, so for example, some of the references are here if you want, but what people sort of in 2000s or so eventually sort of came up with a coarse-grained description of this velocity field. Essentially, u is your bacterial velocity, the coarse-grained velocity, not of the individual. And then you have an equation which looks suspiciously like the Navier-Stokes, my comfort zone. Suspiciously, that's because it has all the wrong signs, because you need to, the modes are not stable, etc. And most interestingly, and this is the only thing that we'll worry ourselves about in this talk really, is the fact that you have this term alpha. Alpha will be negative for a bacteria. So essentially, your bacteria are swimming, and they themselves, because they're self-propelled, they inject energy back into the system for which I'm writing down this coarse-grained fluid description. Tapomoy, yeah.
Yeah. So interestingly, so these experiments, these are very short time experiments, right? So they are very. Okay, so I think at some point.
It's the state of the bacteria, don't worry, yeah. I can hear you. It sort of swirls and then there, yeah. So we didn't exactly observe that, but there were dead patches that we initially had seen, which was when that cover slip was put on top of the bacterial film. There was some element of dirt somewhere, but not exactly the one you're talking about, whereas that's a much more sort of natural phenomena. In our case, it was debris. This for sure we haven't seen. But I can show you, maybe we missed it, I can show you the raw data. Okay.
I have a very simple question
Yes.
about the equation. So divergence of u equal to 0, so what does that signify?
That signifies that we are cheating a little. What that signifies, so the fact that we are assuming that the velocity field is incompressible, it's an assumption which seems to work. I mean, it's a, we can go through the algebra later, which seems to work when the suspension is quite dense. So for dense suspensions, and that's why I sort of stressed the word dense a few times, the incompressible constraint seems to be a good constraint to have.
Are dense, then density fluctuations are unimportant, essentially.
Exactly. Or we hope they are. Yeah, that's exactly. All right. So in this talk, what we will do is we will treat this bacterial suspension that you see here, that's from our experiment, as a continuum two-dimensional fluid which satisfies this equation. And what we have here, so this is from our sort of not so recent anymore paper. What you have here is this is a solution of this equation for a given alpha. And again, as before, visually they seem to show a very similar phenomena. So for what will
I'm the online participant. So here, like what you have done is like you have taken a cover slip and then you have put the solution containing the bacteria, and then, I'm sorry, you have taken the slide, you have put the solution containing the bacteria, and then you have covered it, is it?
Yeah, I mean, that's just for experimental reasons, a cover slip. I mean,
yeah, but like, how did you ensure that it was a quasi 2D and not like a 3D? Because like thickness is, measuring the thickness could be tricky, no, that scale?
Yeah, but what you can do is you can look at the optical density in some sense, and so you can sort of assume you can actually measure in some way the thickness, and essentially what we find is as you sort of go in depth, you quickly reach the bottom. So essentially, you're not going through a strong depth. So we actually did some experiments with 3D drops, which, you know, I'm actually not going to talk about experiments at all because we are still struggling with it. So we've also looked at some 3D, more three-dimensional drops in wedge configurations, etc. But this is really quasi 2D. You just sort of layer it.
And just another question. So the video which you are showing is the video from the bulk, no? So edge is not there in this, boundary is not there.
For the simulation, we will do what all good turbulence people do. We'll use periodic boundary conditions, which is code word for saying that you're looking at the bulk. For this, the sort of movie from our experiments, this is still far away from the edge. I think you're right. Yeah.
Okay. Thank you.
You don't see the edge. Okay. So what we, sorry, just so that we have some sense of numbers for our theory, which is what the talk will be about, you'll see that I'm going to vary alpha, the only thing that enters our game, which is the degree of activity, from -8 to -1. So what we know is that it sort of roughly corresponds to, you know, typical swimming speeds between 75 microns per second to 10 microns per second. Those are the sort of range of swimming speeds that experimentalists have reported across a variety of papers. But I'll come to those comparisons in a bit. So the first thing that one notices is, trivially, is, and now I've moved away from our experiments, is that when you solve this equation and you start changing alpha, so this is a less active suspension, more active, even more active, understandably the flow looks different. The flow starts to sort of become more violent, as it were. So what we wanted to ask, and that's where the sort of inertial turbulence thing comes in, are essentially two questions. Hopefully I'll be able to get to both of them. The first is, in what sense are these low Reynolds number flows turbulent? That's because, classically we associate turbulence with a high Reynolds number phenomena. And secondly, how is this emergent complex flow beneficial to the bacterium? I'll sort of skip over the second question, but I'll focus on the first question a little more. All right. So by we, I'm sort of using royal we. So this work was essentially done by former postdoc Siddhartha, who's right now visiting University of Nice and will move as a faculty to Kanpur shortly, IIT Kanpur. Rahul Singh and Martin were my students. Rahul is now a postdoc at IISc Japan. Martin's a postdoc in Italy at the University of Genoa. And if you want more details, so essentially I'll sort of basically cover the work that were reported in these papers. All right, so change of tack, because we wanted to ask the question, in what sense are these flows turbulent? This is not a turbulence audience, so let me sort of spell out what I mean by real turbulence, if you pardon me for ascribing high Reynolds as the real stuff, and what's the sort of litmus test that we want to do. So turbulent flows are, of course, commonplace, and you see them everywhere. Most flows in nature are turbulent. And so fully developed turbulence has these sort of telltale signatures. They are chaotic, they're irreversible, that's because there's finite viscosity, of course. They're intermittent, and they have multiple length and time scales. So let me the chaotic and the fact that it's irreversible is not something that's going to surprise you. Let me explain a little bit what we mean by intermittent. So this is a good sort of graph, or even this, to look at the question. So this is a measurement, I think, from a wind tunnel of the rate at which energy gets dissipated in a high Reynolds number flow. So for most sort of systems that you will be familiar with, you'd assume that the dissipation rate is kind of constant. So you inject energy constantly, you should dissipate energy constantly across time. Turbulence is a very special beast. If you actually measure this, what you end up having are these strong spikes followed by very quiescent behavior. So there are times, there are long time windows, and this is true if I took a spatial measure of this object, where nothing happens, and then you get a big spike in the dissipation, then again things are quiet. This is one of the ways in which we'll quantify these things a little more as we go along. But if you want to think of intermittency, you can think about the fact that signals in turbulence have this sort of on and off behavior. You can, this, for example, from Antonio's work, is a sort of passive scalar. So think about dye, dye in a turbulent flow. And what you end up having are these sort of strong boundaries between where things are concentrated a lot and where things are not concentrated a lot. So all of this sort of gives rise to these two sort of well-known effects in turbulence. One is that turbulent flows are scale invariant. What I mean by that is if I measure the kinetic energy across scales, which is best done in Fourier space, so I'm going to measure the energy spectrum and the distribution of kinetic energy across Fourier modes. What we end up having is an intermediate regime in K space where there's a power law. So that's what scale invariance really means. So there is no scale in the problem. Furthermore, what people in turbulence know, and this goes back to Kolmogorov's sort of seminal work in the 1940s, is that this power law has a scaling which is with an exponent which is universal. The exponent is -5/3, it's k -5/3, but the number sort of is important. But what you should remember is that if I were to do my experiments in a wind tunnel in Göttingen, or if I were to send a drone up in the atmosphere and make measurements, or on my computer, I would always get an energy spectrum which has the same power law k minus 5/3. So there is a universality of scale invariance. How confidently I can measure how big this range is over which I can get the power law k minus 5/3, that depends on Reynolds number and other things. But the fact that there is a k minus 5/3, there is universality, is one of the fingerprints of turbulence. The other fingerprint is the following, is that if you measure the acceleration statistics in turbulence, if you measure the PDF of, let's say, the difference of velocities on over a given length scale R. I'm being a little fuzzy here because I don't want to get technical. So, you take the difference of velocities between 2 points separated by a distance R, you do it repeatedly, you plot the PDF of that, and many other variables, observables in turbulence, in high Reynolds number flows. What you end up getting are these big fat tails. So there is a finite probability of these very extreme events. Fat tails means that you get anomalously large values, but with a finite probability. So that is another way to think about intermittency. So inertial turbulence, if you ask some of us, we would say that the key fingerprint which distinguishes itself from other non-equilibrium systems would be the universality of scale invariance and the fact that you have large tails in whatever you measure, acceleration, velocity difference, gradients. What about bacterial suspensions? So this is early work. So for example, this is the work of from Bratanoff, Yenke, and Fry a few years ago, where they showed that if you measure the same object, the energy spectrum, the distribution of kinetic energy across Fourier modes, and you do it for different activities, so these are two different activities, you get different exponents. Doesn't happen in turbulence. Whatever be the Reynolds number, however, you'll always get the same exponent. And then in the sort of 2012 paper, they had measured the velocity gradient of these bacterial suspensions. And again, they found everything to collapse to a Gaussian, no large tails, no intermittency. So what these sort of studies would suggest that if this was the yardstick for saying if a system is turbulent or not, then certainly active suspensions with bacteria are certainly not turbulent.
So just a clarification.
Yeah.
I mean, if we compare the bottom two plots,
yeah.
So if you look at the y-axis, like this is like 6 orders of magnitude.
Yeah.
Means, so maybe like there also, if we can,
possible. Good point. Possible. We'll see actually a little better with this data, and the fact that this is Gaussian is actually solid. I'll show you that this Gaussian is really going to be solid. But that's a good point. I mean, it's good to look at the y-axis, but there have been other data which go a bit longer. All right. Yeah.
Sir, in the last slide, like it was mentioned that in case of turbulence, we get a steady state. How can we understand that? Like.
Oh, okay. We are going a little further away, but that's all right. So what we mean by a steady state in turbulence is the following. It's a non-equilibrium steady state. So for example, if you were to draw the total energy versus time from a wind tunnel, you wouldn't get something which is flat. What you'll get is something which goes up and down. But if I take long enough windows and calculate the average, so what I'll get here will be what I'll get here. How long this time window should be to get to make the average depends on something which are slightly more technical in the turbulence literature. But how do you get a non-equilibrium steady state? The way you get a non-equilibrium steady state is the following. We are injecting energy in the flow, right? It's as simple as taking a cup of tea and stirring it. All right, if you like sugar in your tea like I do, so you stir it. So that's how you are injecting energy. Now, because of the nonlinearity, the energy gets transferred to smaller and smaller scales till it gets transferred to scales which are small enough for viscosity to be important. And that's where the energy that you're pumping in at large scale is sort of sucked out by viscosity, converted into heat at small scales. So on average, for a non-equilibrium steady state, on average, over a long enough time window, the amount of energy you've pumped in at the large scales is equal to the amount of energy you're sucking out at small scales, right? That's a sort of quick answer to a more difficult question.
How are we sure that we do get a steady state here? It might be possible that we don't get steady state.
By here, you mean in turbulence? By measurements? So you measure things long enough, you roughly have an estimate of the time scales which are involved in the problem. So you're going to measure multiples of those time scales till you actually see the energy sort of fluctuating, but sort of constant. You actually see the formation of an energy spectrum, which can be measured both, in an experiment. In my code, that's easier to do. You can measure the energy spectrum, and you can see the K-5 third, et cetera. Okay. Thanks. Yeah, while you ask, let me try to find my pointer. Yeah.
Yeah, so is intermittency a consequence of scale invariance?
No. So the question of the origins of intermittency is still shrouded in mystery. I mean, it's sort of related, it probably has to do with the fact that there are questions in high Reynolds number flows which are probably interlinked and shrouded in mystery. I'm sort of going further and further away from the talk, which has to do with the fact that probably there are finite time singularities if intermittency related to that. So we can have a discussion on this, all right? But there isn't a quick answer to your question. Is there a microscopic theory about why turbulence is intermittent? The short answer is no. Yes.
I have a question. Maybe it's slightly off topic, but maybe say a few words of how do you measure an energy spectrum in an experiment? I mean, I understand in simulations you'll have velocity data and so on, but yeah, maybe just.
So in an experiment, what you do is, there are several ways to do it, but one way, for example, you can stick a hot wire anemometer in the flow, which is at one single point, all right? And then what you can do is you can calculate the velocity differences across scales by using what's known as the Taylor's frozen flow hypothesis. So you assume there's a mean flow, etc. So what you can measure in an experiment is certainly fluctuations of the velocity field at a given point. Now that is a temporal measurement, which you can then convert to frequency space, and from there you can calculate the energy spectrum in an experiment. So you can measure the temporal fluctuation quite easily. There are sort of other ways also in which people do it. Yeah. Okay. In numerics, you take the velocity field, do a Fourier transform, and take the mod squared of the field. As you said, it's trivial for me to do. All right. Okay. So I don't really need to finish the talk, so I'll sort of give you the basic idea. All right. So, okay. So where were we? All right. So in 2022 or so, we were here, and the question that we wanted to ask was, then why do people call this suspension turbulent? So let's try to look at that question. So this is the sort of punchline of this work. So you can look up the details. So this is from a few months ago. What we sort of find is that there is a critical activity. So you take your bacterial suspensions. Sankar was talking about suspensions where you put in more alcohol to slow things down. So you take a bacterial suspension, you feed the bacteria well enough so that it starts to become more and more active. So in words, what we find is that as you make these suspensions active beyond a critical activity, and I'll be a little more careful about the word critical when I come to the next set of data, if you're coming from a sort of critical phenomena background. So what we've seen is that when you sort of push the bacteria beyond a certain activity, then an approximate scale invariance emerges with a universal scaling exponent. So what we mean by that is that if if we extend Batonov, Yenko, and Frey's work, and we push the activity even more, eventually after a point we should see a k minus whatever, and that minus whatever will not change if I keep on increasing activity. Okay, so that's the sort of bottom line to this. So I should add a caveat that these are consequences of the equation of motion. We have some experimental evidence, which I will show, but we need some more experimental support. So as I said, at some point, I'll forget the bacteria and I'll just play around with the equations which they're supposed to follow. So, okay, definition. So this is how I define the energy spectrum. So I'll go through this, but in case you do not follow the next couple of steps, don't worry, we'll come to the final result. Never mind how we got there. I mean, except let's hope that we got there correctly without mistakes. So what we can do is we can define the energy spectrum. That's just the sort of UK hat. And the ansatz is that it scales as k to the power delta. Remind you, inertial turbulence, delta is always minus 5/3. Bacterial turbulence, Frey and his group had shown that this delta varies as a function of alpha. That's the sort of central point. So then what we can do is, and this is a sort of field theoretic technique that one can use, essentially we take the governing equations. This is a nonlinear equation, so it's not amenable to analytical solutions, but what we do is we keep on multiplying these equations with u's and u's and u's and u's till we end up having 4 u's correlators, which are u's, and then we use the standard Cumulin thing, which is to break up 4 correlators into products of 2 correlators. So that's essentially the closure model. I'm not sort of going to discuss too much of the technicality, but I can tell you the following. So once you play this game, and this is the effective equation, so when you play this sort of closure game, you can write down an approximate equation, assuming the closure to be valid, for the energy spectrum Ek, and you connect it with what's known as pi, which is the flux of energy going across the Fourier modes, right? So the energy spectrum is the distribution of kinetic energy across Fourier modes. The energy flux is the amount of energy which is going from the left to the right. That's all. So then one can sort of solve this equation analytically, and then one can make certain suitable ansatz on it. And essentially what one is able to get at is that for activity, for systems which are less active than this critical activity, the reason why the greater than sign is, it's not a typo, but alpha comes with a minus sign, that's all. Then you are able to show that this exponent is indeed alpha dependent, exactly what Batonov, Yenko, and Frey had shown. In fact, this is really reproducing their results. All right. However, when you postulate that there is a certain there is a critical activity, which you can actually, again, from this model, you can analytically see what that is. You can end up showing that the energy spectrum is k minus 3/2. So here the energy spectrum is k to the power delta, where delta is a function of activity. When you cross the threshold alpha c, you end up with a universal behavior of the spectrum, which is k minus 3/2. So for those of you who want to know exactly where alpha c comes in the analytical calculation, we'll sort of discuss it after the talk, because probably it's sort of, put all of you to sleep. Yeah.
So yeah, great. So the low activity, see one scaling behavior, and then if you have high activity, you have different scaling behavior. And here you are considering both things as a continuum fluid model. But if I have a widely distributed bacterial or agent suspension, which has different mix of activity, should we expect that there will be a high activity zone which will flow much better, and there will be patches of low activity zone which will be sort of frozen? Is it
Excellent. We do not know, but the epilogue of this talk is exactly on that point.
Okay.
Which is why Kunal's sitting there. Okay, so it'll come. We don't know the answer to the question, but we are exploring that. So it's in the sort of epilogue of this.
Okay.
Great, thanks.
Thank you.
Okay, and theoretically, we sort of predict from the sort of equations that the transition happens at -10, alpha c -10. Y -10 comes out from the algebra. All right, so at this point, it's good to recall that Bratunov-Yankov's results were for alpha, which were far away from alpha c. So nothing inconsistent with Irwin's results. All right, so to cut a long story short, we then actually do the simulations from our hydro equations. We measure delta. For low activity, you see delta is a function of activity, the state of my laptop right now. And when the activity becomes large, delta freezes to a constant. I'll just run and get my charger. You have one? Okay, great, thanks, Rajesh. All right, what we do see is that from our numerics, the transition seems to happen more at -5 and not -10, which was our theoretical result. We tried our best to see if we missed on a factor of 2 somewhere. We didn't find it. So, c'est la vie. All right? Good. So, what happens to intermittency? Yes.
Alpha means this friction term.
Yeah, so positive alpha is something that theorists sort of use. It's really a frictional term. But
okay, so there was, how can you see this bacterial turbulence there?
No, you don't. I mean, as I said, the equation admits negative alpha. So, as I said, at some point I'll use. So, negative alpha is the one which an experimentalist should really compare with. It worked, Rajesh? We'll find out. It'll be a natural cutoff. Let's see who goes faster. No. I guess so. I plug it in a different one, but mine is not a USB. It should work. All right. So now let's look at the question of intermittency. You remember the question of intermittency had to do with this question. So what we did was, so what's a good sort of visual way to think about intermittency? As I said, intermittency is a shorthand to describe a whole sort of very interesting phenomena in dynamical systems, non-equilibrium systems. For this, one way to think about is you look at the vorticity field of your suspension, curl of U, and then you sort of visualize it by suppressing values which are larger than some value. So if there are no extreme events, if you sort of, on the left-hand side, I've just plotted things where the omega is only for stuff which is larger than 6 omega RMS, you see nothing. So certainly the flow is non-intermittent. So this is values of alpha, which are consistent with earlier work, which also reported non-intermittent behavior. However, when you start when you push alpha beyond the critical alpha, you start to see stuff, even when you sort of filter out your vorticity field over the threshold. This can be done much more sort of technically, more quantitatively. So here's, for example, I think you were asking, right? So here's a plot of the same PDF, but now with a larger Y range. So at mildly active suspensions, things fall into a Gaussian. As you push things just beyond the critical activity, you end up getting fatter tails. And what we are able to do is to sort of look at the kurtosis, which is technically the quantitative way to measure whether a system is intermittent. The kurtosis is essentially taking ratios of moments of various powers. So take the ratio of the fourth moment with the square of the second order moment. If things are intermittent, this thing will go away from 3. And this can be scale dependent, alpha dependent, etc. All right. So again, the bottom line is that the system is certainly intermittent when you push beyond alpha c. I have about 10 minutes, right? Yeah. Okay. So finally, what about chaos? What about the chaotic nature of this flow? So here we used a sort of different approach. It's an interesting, I shouldn't say we think it's an interesting approach, might be the appropriate way that we develop for certain other systems in condensed matter in these papers. So essentially what we did was the following. We take a configuration of the bacterial field, so it's an omega field. We make a copy of it, an identical copy, but in the copy, we add a small perturbation at the center, right? So if things are chaotic, then if I subtract these two fields point by point and then integrate it, if things are chaotic, this integral should explode exponentially, right? And if things explode exponentially, I can calculate the growth, and that's the Lyapunov exponent, or the largest Lyapunov exponent, if you want to be precise in the sense of dynamical systems. And that exponent being positive means things are chaotic. In turbulence, when you measure the Lyapunov exponent, we know that the Lyapunov exponent grows with Reynolds number. Mean field theory suggests that it grows as square root of Reynolds, but there's a correction to it, etc. It has a long history. So we are essentially going to measure the Lyapunov exponent as a function of activity with this game that we sort of developed in this and earlier papers. So how does it look like? So you begin with a small perturbation at the center, so low and high activity, and then it starts to grow. And you can immediately guess which is the more active system, or which turns chaotic much more quickly, because then it starts to resemble the original flow. So we are able to actually calculate this. It's what's known as a decorrelator, and we essentially find that there is a positive Lyapunov exponent, and that positive Lyapunov exponent actually saturates at alpha c and does not grow unbounded. This is quite different from high Reynolds numbers, where the Lyapunov grows in an unbounded manner. All right, so this is sort of, I apologize, but I sort of try to summarize, what we have been doing with these suspensions from the tools that we are familiar with in high Reynolds number turbulence.
Can I ask a question?
But yes.
Just a quick question. So on the Lyapunov exponent, so is it true that you have?
It's a two-dimensional system, so the way you're thinking about it is going to be 2, where λ1 will be minus λ2 because of incompressibility. But here we are sort of looking at, in some sense, the largest one. Huh? So what we are measuring is essentially the Lyapunov exponent that you're going to associate with the decorrelator. Yeah. No, so no. So the way we get it is the following. I mean, this is a method that was developed in ICTS by many of us, but led really by Shubro. This is an approach known as the decorrelator approach. So again, the genesis of this goes to certain problems that people did in quantum field theory, which was things like the out-of-time ordered correlators. But for classical system, all it means is the following. I mean, I'll explain it as simply as I can. You take a configuration, you make a copy, all right? So in the copy, at one point, you make a small, tiny little change, all right? And now you calculate the difference point by point between these two copies, all right? So maybe it's, for example, if you have a bunch of spins like this, right? All right? You make a copy of this configuration, identical, but let's say you tilt the spin in this direction, right? Or in our case, I have the flow field. I make an identical copy, except here I make a little change, right? And now I'm going to calculate the difference between these two fields, all right, at every point. At t equal to 0, the difference will be 0 everywhere except at the center where I've made the change, right? Now, and then I evolve these two fields, which follow the same equation independently. As it evolves, the fact that there was a slight difference here, that information starts to propagate. So after some time, the difference between these 2 points will no longer be 0, but it will be finite. Now I can then I can integrate things over, and maybe the rest I can tell you, but that's the idea. And so you are going to see how this difference sort of grows in time, whether it grows exponentially. If it does, then you have a Lyapunov exponent. Right? I hope, yeah. All right. So we've sort of skirted around the question of, are these bacterial suspensions really turbulent? Let's sort of, for 5 minutes or 7, whatever, dwell on the fact that how is this emergent flow? I mean, the individual bacterium presumably doesn't care whether the scaling exponent is -3 or not. I have no idea. I'm not a bacterium, but I assume it doesn't care. So what are the implications of this critical activity for the bacteria itself? And the way, the naive way that we tried to look at this question was to ask, is there an advantage for this emergent flow for an individual in terms of, let's say, foraging? So can it use the fact that it is in this bath to move around much quicker? All right, so what we are going to discuss is what is the implication of mixing. So to do that, what we do, I mean, the way one does normally is to take this flow, but now I put in tracer particles. Tracer particles would be like in an experiment if you put a blob of dye, and then you see how the dye sort of moves, right? So these are my dyes, they're sort of helpfully colored. So these are for different activities, and they just tell you how a tracer in this bath will start moving. What we found was a very interesting behavior. What we found was, so this is a plot where I've shown trajectories for 3-4 different levels of activity colored in different ways. For visualization, we've just taken all the trajectories and put it in the same origin. If you were to notice, you'd see that at lower, when things are not very active, these things are meandering, just like a random walk. However, when things cross alpha c, which is -5, then you have trajectories or a bunch of trajectories which do not meander, but they actually go in straight lines. And you have a bunch of trajectories which does the usual Brownian stuff. So beyond the critical activity, there are trajectories which are both persistent, and then there are trajectories which are diffusive. So let's not, we don't have time to actually see where they come from, except if you want, let me highlight Dhananjay's paper, which was some experiments that he had done. I'm not involved in this, where he found stuff that we had seen so you can discuss with Dhananjay. So what are the implications? Let me just sort of ignore if you want, you could look up or we can discuss why you have this separation of trajectories, but let's look at one specific quantification of how this sort of helps the individual bacterium. So the implication for this, for statistical physicists, is to actually go ahead and measure the mean square displacement. So we can measure the mean square displacement in this flow, and we know that the mean square displacement should be ballistic at short times, and at long times it should be t to the power xi, where xi1 being diffusive and less than 1 greater than 1 subdiffusive or superdiffusive. So what we find is the following. So this is at low activity. What we find is that indeed the mean square displacement is t squared followed by t. No surprise, this was reported earlier. So this was Ashwin Joy's group at IIT Madras. But even before that, there were a bunch of experiments which actually sort of claimed that you get this diffusive behavior. But when we pushed our activity, so this is low activity, T, but when we pushed beyond the critical activity that our theory suggests, we find that this system becomes super diffusive, or t to the power 4/3. The actual exponent doesn't matter as long as the fact that it's sort of, the actual exponent matters in a different way, but not for what I'm saying right now. The interesting thing was that when we found this, we sort of looked around and we found that an earlier work by Ariel and others from 2015 actually was one of the few experiments which sort of claimed that they found super diffusive trajectories in bacterial suspensions. And then because we had this cookbook in which we can compare our alpha to the actual swimming speeds in experiments, we realized that those experiments were done with bacterial which were fed enough sugar, pastries, what have you, for them to be active beyond the alpha C that we had predicted, whereas the experiments which reported diffusive behavior were done with suspensions which were still well below that level. And again, just to sort of, because this made us feel happy that Dhananjay, I hope his experimental results haven't changed, but when we saw this paper on arXiv, where in their set of experiments, they also see this crossover to the fourth head behavior. All right, so I'm nearly done, but all that remains to convince referees and friends is the fact that is this super diffusive behavior kosher? And there is a nice way in which one can do it. So typically, the super diffusive behavior is associated with Levy walks in the system. And you can sort of do the full Levy statistics, which provides an independent bootstrap to know whether the exponent that you measure in your super diffusive system is the right one. Let me not go through this. It's late in the day, and there's still one more talk left of Rajesh's. So in case you sort of want to ask me later, we can discuss how you make the connections between Levy walks of bacteria with superdiffusion. So with that, and also Animalist, first passage, but let me kind of end here by saying what we have. What we have is the following. Again, to restate what we discussed, that what we find, at least in the equations which seem to be the right equations to look at bacterial suspensions, plenty of caveat. Yeah, sorry, Tapomoy.
Sorry, it's a probably very naive question. So, so when you are looking into this transition to super diffusive behavior, is it associated with some sort of length scale where like this turbulent flows are happening? No, right? Because if you put like obstacles, if you do this thing in a periodic obstacle things, I think the emergence of super diffusivity happens even much faster.
Oh, that's interesting. I should ask you about it. But what we have done, what we think is the reason is the following. I mean, the part that I skipped is that beyond alpha C, the flow reorganizes itself and a new structure emerges in the flow, which we call streaks in the paper. Mm-hmm. And that's something that it seems that Dhananjay has observed in his experiment when I was looking at his
paper. Do you think if I put like pillars in the flow, that alpha C changes at that point?
This I don't know, actually.
Okay.
I'll come to that alpha variation in a minute just to flash it, but I don't know. But maybe we should discuss
that. That'll be amazing.
Yeah. But since you brought it up just briefly, so beyond alpha C, the flow is no longer vortical and straining, but a new structure emerges. We don't know why it emerges. We see that in our calculations. Dhananjay seems to have seen it in his experiments, which resemble, if you like, the laning kind of patterns that soft matter people are familiar with. So what happens is, when you have traces which encounter these, they tend to whiz past. So, so the superdiffusion is born out of Levy walks. The Levy walks are mediated by these emergent structures in the flow. And sort of one can bootstrap oneself and sort of see that the Levy picture is correct, because mathematically you can calculate the Levy statistics, the exponents of the Levy statistics, and tie it with the exponent of mean square displacement. All right, so just to finish, so what we now believe to be true, at least for the equations, if not for the real bacterial suspension, is that there is an emergent universality beyond the critical activity, and that's accompanied by the onset of intermittency and maximally chaotic states. This is the point that I just mentioned, Tapomoy, in answer to you, that there is these novel streaks which come about, and there are implications for pair dispersion, pair statistics. What's also interesting for people, sort of glassy-ish people like Rajesh, is that we sort of went ahead and looked at the ensemble of trajectories and found something akin to a dynamical heterogeneity in the way the trajectories separate out, exactly as you guys know well. Okay, so what's the next stage? So the next stage that we are trying to understand is whether these flows are multifractal. Again, that's the turbulence signature. The experiments that I showed you are going on with polymer additives. How does the mean square displacement change, etc.? Because we know a lot about what happens in viscoelastic flows and elastic turbulence. So, is there something similar to that? And then right now, Kunal, who is sitting there and looking very shy, so he's a sort of graduate student who is doing he's doing a coursework. So this semester he was doing a theory project with me, and he was actually interested in this question of spatially dependent activity that Tapomoy you were talking about. And he set up several configurations. One of them is this. So you have a little patch in the middle, which is highly active. At the edges, less active. What we are trying to understand is there a spill-out effect in which this little patch in the middle can try and generate flows outside this? Again, in high Reynolds number turbulence, this is an interesting problem. How do you generate turbulent hotspots when there is none? That's what Kunal is trying to look at, and he'll soon have Lagrangian statistics for this and answer. And then also recently there was this paper by Irwin's group, which has also sort of looked at a peripheral question about spatial dependent activity. So that's what we are now sort of trying to kind of wrap up this story. Okay, with that, I'll end, and thank you again for your patience and time. Thank you. Now you can answer all the other questions now that the recording has stopped.
So I want to ask, what is the limitation of simulation in terms of alpha? I mean, can you go much negative after that?
Yeah. So, you can go as, people doing simulations are nice guys, right? So we can take alpha to be as negative as we want. In fact, there are a couple of very nice papers by Martin James, my former student, who's the author of most of these work, where he had looked at the phase diagram of these systems